Good afternoon. My name is Cory Hinz. I'm the Director of Engineering at THESYS C&D Bioprocess. You may also hear us called Asahi, AKB, AK Bio. I'm going to talk about optimizing an oligo manufacturing process. As we all know, why we're all here this week is that oligos are one of the most promising therapeutic modalities and are expected to continue to be so. So, tightly controlling these processes and gaining as much efficiency as possible is of the utmost importance. So, here it is. So a well-controlled process has many benefits. We've got better efficiency, which is going to give us better purity and yield. We get more oligo. And if we have shorter processing times, that means that we can run more batches in a given period of time, like a year. On the other side of that, if we have a poorly controlled process, a process with a lot of variability that we're not able to quantify or manage, then we're going to have lower efficiency, or we're going to produce less oligo, and our machines are going to be tied up for more of the year. We'll be able to run less campaigns. So let's look at an example. If we take a 20 mer molecule, and we've got a coupling efficiency of, let's say, 99.5%. If that drops 1% to 98.5%, then we lose over 15% of our purity. And that compounds because for a 20 mer, we've got 19 couplings that we're achieving that efficiency at. So while process control and tight control is important for any manufacturing process, it's of the utmost importance, particularly for synthesis. So before we get into the details of optimizing the process, I'll introduce my company, THESYS C&D Bioprocess, briefly. We'll take a quick look at the manufacturing steps that go into an oligo product, and then we'll dive into some ways that we can harness the technology available to achieve those steps efficiently and well. So about THESYS C&D Bioprocess. I myself come from the fluid management division, and we're part of a diverse yet related family of divisions. So we've got our purification business unit, where we've got virus removal filters, microfilters, consumables, biosafety testing services, and then we also have a biologics division that does process development and manufacturing for GMP. Now, within fluid management, we have 4 primary brands. We have THESYS, which is our oligo manufacturing technology. We have Motive, which is our buffer formulation equipment that can really be implemented in a variety of different applications. Cursive is our chromatography equipment, and that's purification not just for oligo manufacturing, but for other downstream applications as well. And finally, we have our Vantage brand, which is related to filtration. And this is where we have some overlap with our purification business unit. Our automated equipment is compatible with the consumables that are distributed by our purification business unit. So some synergy there. We pride ourselves on our ability to design, build, and test a wide array of process equipment. We pursue both standard and customized designs. And we pride ourselves also on our top workmanship and attention to detail. Now, there are 8 values that we ascribe to at THESYS C&D Bioprocess. And these are values that we take into account in all the activities that we pursue, and in particular with our customers. Where basically our vision is to be your trusted advisor and to deliver you tomorrow's solutions today. And we're able to achieve our mission by really partnering with you and our others across the industry to make sure that we're empowering you to best as possible produce medicines that patients need and trust. All right, let's take a look at synthesis steps. So first, our upstream portion, to borrow some sort of bioprocess paradigm, our upstream is going to include our synthesis and our cleavage and our deprotection. Now, the synthesis cycle, before I get into the details of these steps, I should also mention that what I'll be talking about today is exclusively flow through solid phase oligosynthesis. Now, there's obviously other approaches that are in development with very promising and varying levels of progress. and will be, I hope, available in the future for a variety of commercial products. But today, the far and away the most popular and most prevalent approach for synthesis is the flow-through solid phase synthesis, and that's what my process steps and the equipment that I'm talking about today will be related to. So first, our synthesis cycle. We've got detritylation is basically regarded as the first step. This is where we're going to remove our trityl group to prepare for coupling. Moving on to coupling is where we introduce the next base in the sequence, and we add that to our molecule. After that, we have oxidation, or in some cases, thiolation, where we fortify that bond. And then moving on finally to capping, which is designed to limit our N-1 impurities to the extent possible. Now, most processes follow some form of this cycle, although there are exceptions depending on the molecule and the manufacturer. After the synthesis cycle is complete, for all of our bases, our molecule is fully synthesized, we move on to cleavage and deprotection. The cleavage is removing the product from the solid support on which it was built, and the deprotection is the removal of the remaining protecting groups on the molecule. After we complete upstream, then we move on to downstream. So downstream includes purification and concentration. And here I'll mention that about half of manufacturing processes also include an initial or crude UF step before purification. In some cases, that can simplify what the purification is attempting to achieve, which is that we're looking to remove N-X and other impurities from our product before moving on to the final UFDF step, where we're going to do final concentration of the product and desalting before the end of the line, which is lyophilization. I won't go into detail on the lyophilization in this presentation. It's a very well-established technology and is not unique to oligos. All right, so now that we've taken a brief look at these steps, we're going to dive into more detail, and I'll start with what I like to call the 5 dimensions of oligosynthesis. So firstly, we have the diameter of the column, and we have the bed height of the column. Now, the diameter is a fixed attribute, and the bed height is generally adjustable, but will be set at a particular fixed value for a given process. So those geometric constraints come from or parameters come from the column. Next, we have the solid support. The solid support gives us the solid support density, which is an attribute of it, and then also how much product we're going to load. So what is the loading of that solid support? And each solid support has a particular capacity, but that specific value is going to enter into this formula here, and together that's going to give us our synthesis scale in millimole. Now, obviously, if you've got any 4 of these parameters, you can find the 5th one. For example, this equation could be rearranged to solve for the column diameter or the ideal bed height given the other values. So let's say we're going to scale up, and let's harness this equation. So we're going to scale up, and we're going to try to keep a few parameters as constant as possible. First, our solid support density, of course, because we're going to use the same solid support at our different scales, and we want to load it the same amount as well. So we have our loading that's constant. And the third one is the bed height. So at a given linear velocity, our bed height represents the residence time or contact time that our product's going to spend in the column, or that our coupling will happen in the column. And so we want to keep that as consistent as possible as well. And that leaves us with our scale and our column diameter. So if we rearrange those relationships, we can come up with a way to determine the ideal column diameter at a new scale. So for example, let's say that we've got a 20 millimole process that's operating on a 10 centimeter column. If we want to scale it up 10 times to 200 millimole, we can see that it's recommended that we use a 31.6 centimeter column. So in this case, we would choose probably to use a 30 centimeter column, knowing that columns are generally available in 5 to 10 centimeter diameter increments. And that means that maybe our scale then is instead just 180 millimole, or maybe we take a chance and increase our bed height a little bit to get more solid support in there. That, of course, will increase our residence time. But there's a lot of different levers you can pull, as you can see, using this model to sort of guide you. All right. So moving on to specific selections of the column and solid support. So we saw how the column and the solid support both contribute in an integral way to our process. With the column, the diameter is the most important and fixed element of the column. The bed height, of course, can be adjusted depending on the amount of solid support being used or the desired bed height. And those are all easily related geometrically. You also want to make sure that your column is compatible with the other equipment you're using, for example, your automated system, and that it can easily be moved around the facility to areas where it will be packed or where processing will happen, and that there's plenty of clearance for that to occur. We also want to make sure that the solid support is going to be sufficient for our process. There's different loading capacities for different solid support products. For example, polystyrene solid support has a higher loading capacity, but it does swell and shrink as we cyclically expose the column to toluene and acetonitrile in our synthesis process. On the other hand, you have CPG, controlled pore glass. This has a lower loading capacity, but it doesn't swell and is capable of, is conducive to longer molecules, basically. There's also the consideration of a base-loaded support, which includes the first base in your sequence, and this could be a way, if that's available for your molecule, to skip one of your coupling steps. And then the other starting material that we want to consider is our amidite, and how our amidites are going to be prepared and stored and integrate with our automated system. Maybe we want to include recirculating ACN drying or positive amidite identification in line, which is tricky but can be done with things like UV absorbance or Raman or FTIR. All right, one column that I want to point out in particular, made by Asahi Kasei Bioprocess, is our ACS Ergo column under our THESYS brand. This is a column that's hydraulically actuated so that it can be quickly and easily set to the appropriate bed height. It has I-bar clasps that hold the column together, so bolt-free disassembly, and it can be easily turned with a hand crank for discharging the solid support at the end of the synthesis. And if you'd like to see a model of one of these columns, please visit us at booth 216 later in the show. All right, so now that we've looked at the solid support, the column, our starting materials, we're going to get into the process now. And this is where we need our automated equipment to perform these steps. So we've got detritillation first. This is where we're breaking the 5' bond and preparing for the next base to be added. Now, this is done generally with a 3 to 10% DCA solution in toluene. And this is also flushed then at a high flow rate to make sure that the DCA doesn't perform any further degradation of the molecule after cleaving off the DMT group. Now, the way that we can do this with our equipment is by making sure that we've got appropriate flow control and instrumentation, UV, conductivity, IR, that we want to be monitoring this step, and that our system's capable of the high flow rates needed for the ACN flush. And this is important, as I mentioned, to make sure that once the DMT group is removed, that there's no further degradation of the molecule from the DCA. And so this means that your equipment needs to be able to flush at flow rates upwards, higher than 400 centimeters per hour in your column. Linear velocity, and that needs to be able to be done with the column in line. So there can't be any column or process piping issues in terms of pressure increase. Your system needs to be large enough to be able to accommodate that high flush that a detritillation step requires. Now coupling. Coupling is where we're adding the next base in the sequence. So we introduce our amidite solution in a number of equivalents, and we also introduce it in conjunction with an activator solution. Now, the activator and amidite will be delivered at a certain proportion that was determined during process development, and this is designed to maximize the efficiency of the coupling. Now, it's important because of this that the activator and the amidite are both reaching the column at the same time, so that none of the amidite is wasted and all the activator is put to its best use. Now, the activator is the less expensive by a long shot than the amidite. And so at large scales where it's hard to get things down to the mill or the second, it's advised to maybe have a little bit of activator get there to the column first and maybe a little bit extra activator at the end, just to make sure that you're getting the best efficiency out of your amidites. Now, this is also the one step in the cycle where we're going to recirculate. Most of the steps are single pass, but in coupling, we're recirculating to maximize, again, the efficiency of our coupling. Some chemistries couple very quickly on a single pass, and some benefit from multiple recirculations. Now, the volume that we're recirculating includes process piping on the system, it includes the column's holdup volume, and includes the hoses in between. And as that volume recirculates, we're going to be able to introduce the amidite solution several times to the column. Now, how can we do this with our equipment? Well, we need to make sure that we're able to deliver the activator and amidite solution together to the column. And this requires that we understand the geometry of our system. Now, the amidite and activator proportion can be somewhere from 40-60 to a 60-40 proportion. And even there are exceptions. And so we need to make sure that we're introducing those solutions with proportional linear velocities. So if our amidite is going to be 40% of the solution, then the amidite should be 40% of the flow being delivered to the column. But the activator and amidite might not be the same distance from the column. Especially for more advanced synthesizers that have a lot of different inlets and can accommodate a number of amidites and a number of reagents. The locations of these ports might vary, or the geometry of your production suite might necessitate that certain things be in a certain place. And this can cause a little bit of a wrinkle in your recipe writing. So you need to understand what those holdup volumes are. So here I'll use an example. So let's say that our amidite holdup volume, from where we introduce that to the system to where the amidite joins the activator, is 200 mils. And then let's say the activator is only 100 mils. And in this example, our amidite proportion is smaller, only 40%, and the activator is the rest. And so in this situation, we would expect that if those two inputs to the system are operating at proportional linear velocities, that the activator is going to get to the column first. And we want them to get there at the same time. So while I'm writing this recipe, I'm going to make sure that the amidite has a head start, basically. And so I'm going to start the amidite first, and the activator will then begin at a later time. Now, how much that delay is in your recipe is going to be related to your system's geometry. Is that amidite at the front end of the amidite block? Is it at the back end of the amidite block? And so it's important to understand that and work with the equipment manufacturer as necessary to make sure that that's understood and integrated into your recipe, again, so that you get maximum efficiency out of your amidite. And one more point about the activator and amidite solution is that you want it to occupy as much of that recirculation volume as possible so that you minimize dilution during recirculation. So what that looks like is, or what that can look like, is using a scaled down approach. And that is to take the holdup volumes that are present on your production scale system, which due to instrumentation and bend radii and line size and so forth, are generally larger than at development scale, and replicate those proportional holdup volumes on your smaller scale synthesizer, potentially by adding extra holdup volume to the loop, an extra piping length, and make them more comparable. And that way, the results become much more comparable between the two scales when you're comparing your final yields. After coupling, we've got oxidation and thiolation, and that's where we introduce either a PO or PS bond. And this is a step which is typically follows coupling, although in the case of oxidation could follow capping. And this is basically backbone modifications. And this is where you would do anything else that falls in that category in your process. Obviously, where there's every day a wider variety of molecules. So I'm using kind of the most mundane approach here of either oxidation or thiolation in this step. And then finally, we have our capping. And again, there are some processes that have found a way to avoid capping, but the idea of capping is that you're introducing a capping A and capping B solution together at the same time. So again, we're going to use some of that strategy from our coupling step. And the capping is designed to terminate any sequences where that most recent base addition didn't take hold. And that will drastically reduce the number of N-1 impurities at the end of our synthesis. All right, now we've completed our molecule, and in some cases, after our final cycle, we'll do a final detrylation or amine wash, depending on the needs of our process. And then we move on to cleavage, where we remove the molecule from the solid support using ammonia or AMA solution. And the deprotection is going to require us to introduce DMSO and heat, hold at a certain temperature for a certain amount of time. And then beyond that, in the case of RNA molecules, we're also going to use what is generally a TEA3HF buffer addition to the process to the product solution, which is going to require quenching afterwards. Now, this addition is highly exothermic, and so in addition to chemical compatibility concerns with your C&D equipment, making sure that it can withstand all the harsh chemicals that we're using, that it's also able to help you mitigate that temperature rise of the HF addition. UFDF, as I mentioned, sometimes happens immediately after deprotection. And in this case, we're using a TFF membrane to concentrate and desalt the product solution. And this will be done again at the end of the manufacturing line as well. There is one way to combine unit operations, which is, of course, always a plus. And at Asahi Kasei Bioprocess, we have a unit that combines cleavage and deprotection with crude UFDF and can perform these operations in sequence on the same piece of equipment. It's designed for use in hazardous areas as a single low capture point to get all of the product out of the system. And it's compatible with a number of different TFF membranes that are currently used for oligo products. Purification. So this is, I think, a pain point in most processes. It is a bottleneck, and it is one of the more complex elements of your oligo manufacturing. Now, on the equipment side, most equipment is generally flexible enough to accommodate the different types of chromatography that would be employed. And here we're also using, we're done with our synthesis column, we've moved on to our chromatography column. And so we're going to need to make sure not only of chemical compatibility, but that we're able to deliver the right solutions and the right flow rates, including linear gradients of our mobile phase, and that our column has very efficient distribution throughout its full cross-section. I mentioned final detritylation. Depending on how your synthesis ends up, you may choose to leave that trityl group attached or not for DMT on or DMT off purification. And that can be handy depending on the chromatographic modality that you've chosen. That DMT handle can provide, in some cases, a convenient way to simplify your purification. With oligos, we're generally looking at ion exchange chromatography, reverse phase, or hydrophobic interaction. All right. Changes. So I think everyone who has been involved in manufacturing has had to experience, undergo, and manage somehow a change to the process, usually when you least expect it, from any number of sources. And so for that reason, it's important to take into account that your equipment be flexible. So equipment flexibility looks like having wide operating ranges, controlling on more than one process parameter, accommodating variable sizes of filter membrane, accommodating variable sizes of column, designing for flexibility in the core of the design. For example, a recirculation loop where you can swap out piping pieces for different volumes, as we saw how important the recirculation volume is. But at the same time, I'll mention in the same breath that we need to recognize the limitations that exist on equipment. And these are just physical limitations. Pumps generally have very good turn down, especially metering diaphragm pumps that are commonly used in oligo manufacturing. But there are limits there. Heat exchangers, for example. Heat exchangers are typically sized based on a particular design flow rate. And at less than half, or especially less than a quarter of that design flow rate, you can expect the performance of that heat exchanger really to suffer. And line sizes and holdup volumes also come into play. If you have a small column connected to a large synthesizer, those larger synthesizer pipes are going to have a larger holdup volume, and that system is going to represent a much larger portion of your recirculating volume than the column is. And vice versa. And if your lines are too small for a larger process, you may end up with some undesirable pressure increases and so forth. So we want to be as flexible as possible while staying in the realm of reality and recognizing that there are limits to what our equipment can do. And another point is automation. So automation can make our lives easier. We need a platform that it can give us a repeatable and controllable process with user-friendly features, easy recipe writing, easy visualization of our sequence and our live data, customizable batch records, and also making sure that we're GMP compliant, 21 CFR, and everything else that we need in our manufacturing train in terms of those requirements. One platform that I'll mention is Asahi Kasei Bioprocess offers an Ocelot system control. Ocelot system control is a platform that is specifically designed for oligo manufacturing, not adapted from another process, but specifically for oligos, and has some very innovative and user-friendly features for organizing and maintaining your sequence and your recipe. And then one last thing I'll mention is having a an expert equipment partner, someone who knows the equipment and knows the process and can work with you to optimize what you're trying to do. And you can see on the screen here a variety of manufacturing equipment manufactured by a say bioprocess, covering your process basically from start to end. Except for lyophilization. And so for all of these steps in between, we endeavor to be your trusted advisor so that you can have a simplified project management, more straightforward procurement process, and synergy across all of your different pieces of equipment, the same look and feel for all of your operators, and so forth, and that you get that same high quality at every piece of equipment that's part of your manufacturing train. And I'll close by just saying, if you'd like to continue the conversation, please come visit us at booth 216. We've got a little ACS ergo column that we can show you, and a number of other pieces of equipment that we can page through and talk to you about if that happens to be something that you're interested in looking to optimize your process. So thank you very much.
Are there any questions for Cory? Please use the mics in the middle of the screen, please.
Good comment on the possibility of determining each cycle has gone to completion or not. So let's be more specific. For example, coupling. You have recycling loop. We are just continuing the recycling to assume that it's going to drive the reaction to higher efficiency, but it may not be necessary, let's say, after 2 cycles of the loop, and maybe it's done in 5 minutes, and sometimes we're pushing it to 10 minutes or even longer, which is an overkill, and it produces more of the N+1 mer. So do you have any now ability to detect that my concentration of incoming phosphoramidite, let's say in circulation loop number 2 or 3, is the same as the outgoing phosphoramidite solution, so you are able to detect the incoming and the outgoing concentration of the phosphoramidite, and if there is no change, then you can stop that recirculation, which is not necessary?
That's a great question. The instrumentation on the system, it's key to make sure that you have the instruments you need. Our clients make the best use of conductivity, UV absorbance, and density to monitor exactly what you're talking about. Not a chemist myself, I wouldn't be able to speak to exactly how those might be harnessed to identify the changes in concentration. But another pattern that I've noticed that I'll mention is that while PAT is very powerful and can be very handy, we've mostly seen that used at the development scale because it's a little bit easier to validate the fixed times and volumes at the production scale. And so those kind of optimizations are typically done further on up in the process at the development scale and then replicated at the downstream scale. But yes, absolutely, you could harness the instrumentation on the system to determine and not over-circulate when not necessary.
So the data output will allow you to then judge. Is that correct?
That's right. Yeah, because you'll have the live data as well as all of the batch report data that you can export and manipulate to your heart's content.
So that's live, means manipulation of the data. So I can say stop circulation.
Yeah. So if you have the right credentials, you can make the system do whatever you want. But once you've run a synthesis and you want to see, okay, where should I have ended my coupling? You can export that data and analyze it, or you can set up a trigger in the software to say when this particular sensor reaches this particular value, I'd like the process to advance.
Thank you.
Yeah.